Hey guys, welcome to Safi Next. In this video, I am simulating the probability of binomial distribution in Mathematica. The purpose of this video is twofold. Number one, it will let you know how the probability of a given sequence of outcomes varies with the increasing number of trials in binomial distribution. Number two, this will enhance your capabilities of constructing function and writing programs with conditions in Mathematica. So let's understand how can we do that. So here I construct a function named Pn with three variables, capital N, and small p, which describes the binomial distribution. This is the relation for binomial distribution. And the variables capital N, and p stand for the capital N stands for total number of trials, small n stands for the number of occurrences of a given sequence, and small p is the probability of an outcome in a single trial. The number of a given sequence can never be greater than the total number of trial, that is n. So I want to impose this condition on the function Pn through the f function. So here I write in f condition on the function Pn such that the small n should always be lesser or equal to n. When this condition is satisfied, the Mathematica will implement the values of the function Pn, and if this condition is violated, that is, if small n is greater than capital N, the f condition will force Mathematica to set the values equal to 0. If you don't know about the use of f function, I have a detailed video on this and will suggest you to watch that video. Now I want to dynamically simulate the function Pn. For this purpose, I use three different functions. Number first, the table function. I construct a table of values of the function Pn for each choices of n, where n I'm setting for the time being as n equal to 0 to 6 and varies in the steps of 1. Then I ask Mathematica to plot this list of values of the function through list plot, and I use different function within list plots. For example, I ask Mathematica to plot the values of the function Pn from 0 to 0.55. Through the plot style command, I ask Mathematica to give a point of size 0.25 in color red, and then again through axis label I ask Mathematica to label the x-axis with small n and the y-axis with capital P of n. And I set the number of trials from 1 to 5. Now note over here, the number of trials would vary from 1 to 5, and I have set the number of occurrences of a given sequence from 0 to 6. Means the value of small n is greater than the values of capital N. So this function would tackle that increase of small n values in the plotting of this function. And then I use the manipulate command of Mathematica to simulate the values of these tables for the capital value, for the values of capital N, which would vary from 1 to 5. Now if I run this part of the program, it gives me this plot. I add the simulation with respect to capital N by clicking on this plus button. Now you see for capital N equal to 1, there are two possibilities for small n, that is, the small n can take values 0 or 1, and these two values satisfy the first condition in the f function. So Mathematica gives values for Pn for this range and set the rest of the values for small n equal to 0 as per the condition given in the f function. If I increase the value of capital N by 1, that is I set capital N to 2. Now there are 3 possibilities for the value of small n, and look, the probability for n is equal to 0 and n is equal to 2 reduces, while the probability for n equal to 1 has a maximum value of 0.5. If I further increase the values from 0 to 10, the number of values for small n again increases, that is n can take values from 0 to 3, and for all these values as per the F condition we have the corresponding values for probability Pn3. So again, the overall probability for each point has reduced further, but the middle points has highest value 1 for n is equal to, for small n equal to 1 and 2 we have probability nearly equal to 0.4. If I keep on increasing these values, the probabilities of each point changes, and for the maximum of capital N equal to 5, which I have 5 over here, the shape of the probability distribution takes this one. Still, for small n equal to 6, the probability is 0 as per the condition of f function. So now let me change this value to a larger value, that is, let me set this equal to almost 30, and let me set the value of n equal to 30 as well. Now if you look, the maximum value of n, which is 30, is equal to the maximum value of capital N. So for the maximum value of capital N, the probability, the condition, so for the maximum value of capital N, the condition within the f function, the first condition within the f, so for maximum value of capital N, the first condition within the f function is satisfied. However, for other values of n, the first condition is not fully satisfied, and the f function will set the values of n greater than capital N equal to 0. So if I run this function now, I would have this thing. Now look over here, I have for n equal to 1, which is 1 over here, I can have the value of small n equal to 0 or 1, and thus the Mathematica evaluates the value of probability function for this, but set all the rest of the value equal to 0. If I simulate this function and I set this in auto, you will see that how the probability varies. Since the maximum value for n is 30 and now it is taken like this, I can change this. I can spec the implication of f function by setting this upper limit to capital N. Now I restrict the value of small n to the maximum of n, and hence if I run for this case, I would have values like this. That is, the small n can now, for if I add the simulation over n from this button, now for n capital N equal to 1, we have 2 possible values of small n. One correspond to n is equal to 0 and the other correspond to n is equal to 1, where I have limited the value of small n by setting n over here. Now the f function always implement the first condition as it is satisfied as per the choosing value of n over here. If I keep on increasing the value, we see the number of points for probability varies accordingly. However, the maximum now always remain at the center of the values, and if I put this on autoplay, it goes like this. You see that the maximum point reduces with in magnitude as per the probability distribution. Now let us see the normalization of the probabilities in the binomial distribution that I can do by writing this by using this part of the program. Here I sum all the possible probabilities for p equals 0.5 and then construct a table of the values for different choices of small n, and ask Mathematica to plot the values of the list produced through the table command, and finally I manipulate for different values of n, and here I am setting the maximum value of n equal to 60. If I run this part of the program, I get a similar situation, but the probability always stays at 1 now. For capital N equal to 1, we have two possibilities, that is one for small n equal to 0 and the other for small n equal to 1. However, for each case, the probability whether I am taking n is equal to small n equal to 0 or small n equal to 1 or small n equal to 1, the probability is staying on 1. If I simulate this for all the rest of values, you see the points are added at Pn equal to 1, but it always stay normalized. That is, the sum of the probabilities for all the sequences equal to 1. Okay, with that done, I would like to say, if you haven't subscribed to Safi Max, kindly extend your favor by supporting the channel through your subscription. Thanks for watching.